Now in this session, we take an example problem for distillation column control. Now here for distillation column, we have the relation between this top product and the reflux ratio given by this first order transfer function. The column was operating with a reflux ratio of 2, giving a corresponding value of this xd naught to be 0.98. Now the reflux was changed to 1.5 at some point, which is our time 0. We'll take that to be as our time 0, and that was kept at 1.5 for 40 minutes, and then it was brought back to 2 after 40 minutes. Okay, here the gain is 0.1 and this time constant is 12 seconds. So the gain is in terms of mole fraction over the reflux ratio. So that's the fraction over a ratio. So in that sense, it's unitless. The two things you are asked, if xd is equal or below 0.95, that's our what is called off-spec product. And if yes, what will be the amount of the off-spec product? Okay. So we are given the xd naught to be 0.98 and the product rate is 10 liter per minute. Okay. So before going to the solution, just take a look at what does it mean. So we'll have to figure out whether the xd, which is the top composition, will go below 0.95. And second, if it goes below 0.95, for how long it will be below or equal to 0.95. And then using the product rate, we can find out the amount of off-spec product. Okay. So to find out the response of this top product due to the change in the reflux flow, let's just express the reflux in the deviational form, where r prime t equals rt minus r naught. So we'll have this r prime to be as a pulse input, and it went from 2 to 1.5, so there's a negative change. So from 0 to negative 0.5 and then coming back to 0. So in terms of the typical notation of a pulse input, so the m value is negative 0.5 and this capital T value is 40 minutes. Okay. So in the Laplace domain, then r prime s is written as m over s plus m over s minus m over s e to the power negative capital T s. So we'll have negative 0.5 over s plus positive 0.5 over s e to the power negative 40 s. Okay. Now let's look at the response of this. So xd prime s will be then 0.1 over you can write it as so if we take this inverse Laplace, we'll get for this one simply these are k m at this part, so it will be 1 minus negative t over tau, and for this part we will have plus t minus. So we'll have to find out whether this will go below 0.95 or not. Okay. Okay, so we'll have this one, and we need this unit step function because before t equals 40, this part will be 0 and this part will be effective after t greater than 40. Okay. So now to answer the first part, we have to figure out whether the value will go below 0.95 or not. Okay, look at the response. Due to the change in the input, something like this one. Okay, so these are 0, 4, R prime. Okay, and if I take this output to be xd, it will be initially from here at time 0, whatever value it was there, it will come back and then it will go back again. Okay, so you can see if it comes to 0.95 or something like a value like that, it will be before t equals 40. So it will be before t equals 40, because t equals 40 it goes to the minimum, so it will be sometimes at or before t equals 40. Okay, now to find that out, at what time it will go beyond, suppose somewhere here, at what time it will go 0.95, we have to find out whether what will be the minimum value of xd. Okay, so we know that xd will be minimum at t equals 40, that you can see from the response curve here. Okay, so for this case, xd minimum will be, so xd minimum will be xd naught plus xd t equals xd prime t equals 40. Okay, now if your this value, you know, this 0.98 plus, for this case, if I look at, if you plug in t equals 40 here, this term will be approximately 0. You can do the calculation and it will be simply negative 0.05. Okay, so it will go to 0.93. That means there will be off-spec product. So the answer to the first part is yes, there will be off-spec product. Okay, so if yes, what is the amount of off-spec product? Now for this case, let's try to figure out that it went to 0.93 at times t equals 40. So understand that it will go 0.95 at sometimes before t equals 40, and then it will come back at some point. Okay, so suppose you have this time to be this t1, and when it comes back, that's we denote as t2. So if you can find out these two times, you can figure out for how long the product will be off spec. Okay, so for, you know, that for t1, which is less than 40, we have xd plus only this part, because this part will not be valid for this case. So it will be t over 12. Okay, now know that this is our 0.95 we are trying to find out. This is our 0.98, sorry, xt naught, negative 0.05, 1 minus e to the power negative. We are trying to find out t1. So we are assuming at t1 it will be 0.95, t1 over 12. So we have seen how to solve this part, and if we do this, you'll find t1 to be 11 minutes. So now finding out the value for t2. So for t2, which is, we see that it went to 0.95 to 0.93 and came back. So we have the expression for that. We have to use the entire expression for this case. So for t2 greater than 40, we have x dt and the entire term negative 0.05 1 minus e to the power plus now you see that we're not writing this st minus 40, the Dirac delta function, because we are already assuming that t2 will be greater than 40. So this is valid for any t greater than 40. So if you need to find out what will be the t2 for which this will be 0.95, so it will be 0.95 equals the first one 0.98 that will be t2. Okay. Now we have to solve this equation to find what will be the t2. And for this case, you can look at plug in this value for t equals 40 here. It will find that this term is approximately 0. Okay. So if that's the case, we'll have 0.05 times 1, and there is positive 0.05. This term will also cancel. So we'll have 0.98, and this will be negative 0.05. And if you solve this, you'll get t2 to be 46 minutes. So for the duration of spec product is t2 minus t1 is 35 minutes. The amount will be then times 10 liter per minute, giving 350 liter. Okay. So that's take a note that if you try to solve it using taking logarithm, that will not work, and there is no general solution for this. So we'll need to resort to numerical methods. But for engineering calculation, you see that okay, this value becomes 0, very close to 0, and you'll have only this termlet, and you can get a very reasonably accurate solution.